Okay, good morning everyone. I'm Zheng Yuning from Campus Lab of Wayne State University. Today I'm going to present our paper, Understanding the Security of ARM Debugging Features. And this paper is a joint work with my advisor, Professor Fengwei Zhang. Now this is the outline for the presentation. Now let's start from the introduction. As we know, modern processors, normally they are equipped with hardware-based debugging features. For example, we have some hardware-based breakpoints, and also we may have some hardware-based trace components. And to make use of this kind of hardware debugging features, it normally requires us to make a physical connection, like a JTAG cable connection to the device. This is an example of the traditional debugging mode. In this mode, we have a debug host on your left, and we have a debug target on your right. And normally, we connect the host and target with a JTAG cable. Then you can sit in front of the debug host and try to debug the target via the JTAG interface. And in this mode, the host may be malicious. So to defend against the malicious host, ARM designs the debug authentication mechanism. In this debug authentication mechanism, it will decide whether the hardware debugging is allowed or not. So if the hardware debugging is disabled on the debug target, then the malicious host cannot access any debugging features of the debug target. Okay, so this mode has been introduced to the industry for many, many years. But actually, we didn't really see a lot of security research related to this mode. Why? We consider it is because that we have some obstacles for the attackers. First, in this debugging mode, since we need the JTAG connection, so normally we will assume that the attacker will require the physical access to attack the system. And second, we will assume that the debug authentication mechanism will block all the malicious hosts. But do these obstacles really work? Now we will discuss these obstacles in details. First, does it really require physical access to do the hardware debugging? And of course, the answer is not. Actually, we can use one processor on the chip to debug another processor on the same chip. And we refer this kind of debugging as the interprocessor debugging. In the ARM architecture, the interprocessor debugging is achieved by the memory-mapped debugger registers. And if we use this kind of debugging mode, we will not require any JTAG cable. And of course, we will not require the physical access. And then second, does the debug authentication mechanism really work as what we expected? Before we answer this question, I want to introduce something about the debug authentication mechanism. First, I will introduce different debugging categories in the ARM debugging architecture. As we know, when the processor is running in the normal state, the processor will continue executing the instructions pointed by the program counter. And if we use the non-invasive debugging, we are trying to monitor the status of the processor without any control. And if we use the invasive debugging, we are trying to pause the processor to make it running in the debug state. After that, we can change the status of the system. Then, the debug authentication mechanism in the ARM is achieved by a group of debug authentication signals. The debug authentication signals is a group of hardware signals connected to the processor. And it has two different states, on and off. And the on and off status is used to control whether the hardware debugging is allowed on the chip, is allowed for the processor. And if we consider both the secure and the non-secure state of the processor, and also the invasive and non-invasive debugging, we will have 4 different debug authentication signals. And then I will introduce the ARM ecosystem and their relationship with the debug authentication signals. In the ARM ecosystem, we have 4 different roles. We have ARM, we have SoC vendor, we have OEM. OEM means the original equipment manufacturers. And also we have end user. First, ARM will license the technology to the SoC vendor. In regard to the debug authentication signal, ARM only designs the debug authentication signal. And they will not specify any details about the implementation of the debug authentication signal. And then the SoC vendor, they will develop the chips for the OEMs. And for the debug authentication signal, they will implement the debug authentication signal. And also, they are in charge of how to manage this kind of debug authentication signals. After that, the OEM gets the SoC chips from the vendor, and they can produce the devices for the users. And for the debug authentication signal, they are responsible to configure the debug authentication signals. And then finally, the end user can enjoy the device. And in most cases, the user can only learn the status of the debug authentication signals. Okay, that's all about the debug authentication signals. Now let's get to the question again. Does the debug authentication mechanism work as what we expected? Specifically, we want to answer two questions. First of all, what is the status of the debug authentication signals in the real-world device? And also, how to manage these signals in the real-world device? To answer these questions, we performed the investigation to the real-world device. In our investigation, we try to cover different categories of devices, such as the development boards, the IoT devices, the cloud platforms, and also the mobile devices. The last four columns indicate the status of the debug authentication signals in the real-world device. As we can see, in many devices, all the debug authentication signals are enabled. Surprise, huh? And then we answer the second question, how to manage the signals in a real-world device. For this one, we try to survey the publicly available manuals of the devices. And also, we try to find the open source kernels for the devices. For the development boards, we have the manuals. But still, to the best of our knowledge, we can only control part of the debug authentication signals. And also, we find that in some mobile phones, the debug authentication signals is controlled by the one-time programmable fields. But for all the other devices, nothing about the debug authentication signals is publicly available. Now, let's summarize a little bit. First, we don't really require the physical access to use the hardware debugging features. Second, the debug authentication mechanism in the real-world device actually allows us to do the debugging. Then let's see what we can get. This is the interprocessing debugging mode we introduced. Again, you have the host on your left, and you have a target on your right. And you can use the host to debug the target via the memory mapped interface. And in this mode, again, the host may be malicious. Then what will happen? Let's consider a SoC system like this. In this system, we have a host processor, and also we have a target processor. And we have a low privilege resource, and we have a high privilege resource. Here, the low privilege refers to the non-secure kernel level privilege. That is because that in most cases, it requires the non-secure kernel level privilege to access the hardware debugging features. And then the high privilege refers to any higher privilege, for example, the hypervisor level privilege or any secure privileges. At the very beginning, we will assume that the host and the target are both running in the normal state, low privilege mode. Since they are running in the low privilege mode, so they can only access the low privilege resource. Then, we can ask the host to send the debug request to the target. Once the debug target receives this debug request, the target will check its own debug authentication signal. And the privilege of the debug host will be ignored. What does that mean? That means even the host is running in the low privilege mode, and the target is running in the high privilege mode, the host can still send the debug request to the target. But here, for generality, we still assume that the target is running in the low privilege mode. So after the target receives the request, it will turn to the debug state. But again, it is running in the low privilege mode, so it can only access the low privilege resource. To achieve the access to the high privilege resource, the host can then send a privilege escalation request to the target. For example, the host can ask the target to execute the DCPS instructions. The DCPS instructions, they will promote a processor running in the debug state to any required privilege state. And also, when the target receives this request, again, the privilege of the host is ignored. So the target will accept the request and turns to the high privilege mode. That means that now the target has access to the high privilege resource. But at this moment, the host is running in the low privilege mode. The target is running in the high privilege mode. The host still has full control over the target. That means the host can then send a resource request, access request to the target. For example, the host can ask the target to execute some special instructions to access the secure run, to access the secure register or secure peripherals. And again, the privilege of the host is ignored. So the target will just access the high privilege resource and then return the result to the host. And in this way, the host actually gains indirect access to the high privilege resource, although it is still running in the normal state, low privilege mode. And we refer this as the nail gun. The idea of the nail gun attack is to break the isolation of the ARM platform while misusing the ARM debugging features. And in fact, the nail gun can be used to craft different attacks. For example, we implement different attack scenarios like inferring the AES keys from trust zone, like read the secure configuration register, and even arbitrary payload execution in the trust zone. And also, we try to cover different architectures and different devices to verify the impact of the nail gun into the real-world device. We also show that nail gun can be used to extract the fingerprint image from a commercial mobile phone. The phone we choose is Huawei Mate 7, and the fingerprint sensor on this phone is FPC 1020. We choose this phone because the manual and the driver of the fingerprint sensor is publicly available. So it will save us a lot of engineering efforts. In regard to the attack, actually you just need some simple steps. First, by reverse engineering the firmware, we can learn the memory address of the fingerprint data inside the secure RAM. After that, we can extract the fingerprint data with the interprocessing debugging mode of the nail gun. Then, according to the publicly available manual, we can reconstruct the fingerprint image from the fingerprint data. And this is an example of the extracted fingerprint data. The right part of the image is blurred for privacy concern. And the source code and the video demo of this attack can be found on our project website. Also, we have reported our findings to ARM and related OEMs. This is the timeline for our disclosure. Now we're going to talk about the mitigations. Intuitively, if we can disable all the debug authentication signals, the interprocess debugging will not work. But can we simply disable these signals? Unfortunately, no. Why? First, we have a lot of tools built on the debug features. For example, we may have a lot of program analysis tools. They try to use the JTAG interface to monitor the status of the processor. They try to monitor the memory of the system. They try to monitor the execution of the SoC. And if you disable the debug authentication signals, then this system will not work. Second, as we mentioned, the management mechanism of the debug authentication signal is not publicly available. Assume that you have get a Raspberry Pi, and you build your own IoT solution based on the Pi. Now you know nail gun attack. But with all the manuals on your hand, you have no way to disable the debug authentication signals. And also from the view of the OEMs, because they use the one-time program fields to configure the debug authentication signal. So the one-time program feature will prevent them from reconfiguring the debug authentication signals. And also, they may have some additional concerns about the cost and the maintenance. So we will suggest a comprehensive defense across different roles in the ARM ecosystem. For the ARM, we will suggest that additional restriction should be applied to the interprocessor debugging mode. Specifically, when we try to do the interprocessing debug, the privilege of the debug host should not be ignored. They should consider both the privilege of both the debug host and the debug target. And from the view of SoC vendor, we will suggest that they can refine the signal management mechanism. And also, they may deploy some hardware-assisted access control to the debug component. That means they can restrict the access to the debug registers. Also, for OEMs and the cloud providers, we will suggest that they can use some software-based access control. Now we conclude. Here, we present a study on the security of the hardware debugging features on the ARM platform. And our study shows that the safe components in the legacy systems may become vulnerable in the advanced systems. Here, the traditional debugging mode is a legacy system, and the single core system is a legacy system. But when it comes to the interprocessor debugging and the multi-core system, the safe component becomes vulnerable. So we will suggest a comprehensive rethink on the security of all the legacy systems mechanisms. This is the reference for the presentation. Thanks for your attention. I'm happy to take any questions.
If folks have questions, please line up. So one question that I had is, when you reached out to the vendor, what was their reaction to all of this?
Actually, because we talked with a lot of OEM and SoC vendors, but most specifically, the SoC vendor is responsible for the management. So they are trying to restrict the access to the debugging components. For example, the MediaTek, they said that they have some hardware component to define the boundary between the trust zone and the non-trust zone. So they are planning to apply this hardware to restrict the access to the debug registers.
Interesting. And then I guess one other question is, does that solve the supply chain issue? Because right now it seems like everybody in your solution has a responsibility in it. And they're thinking of a different strategy then, or it'll still exist as a problem of supply chain?
Because the management is decided by the SoC vendor. So if the SoC vendor has deployed some defense mechanism, the OEMs can make benefits from the defense.
Okay. If there are no other questions, then let's thank the speaker.
Thank you.